here's another important point. With respect to stretching vibrations and bending vibrations that are present in any given molecule, it turns out that stretching vibrations tend to have a higher frequency than bending vibrations. Now, it's not a perfect separation. In fact, there's some overlapping that occurs. All right, let's look at an example of a molecular compound absorbing IR light. It will produce what is called an infrared spectrum. For example, we'll use a compound whose structure consists of a 6-carbon ring with an external carbon-carbon double bond. This is also called an exocyclic double bond. Now, this molecule has different types of bonds. These bonds are undergoing continual vibrational motion, which includes both stretching and bending type vibrational motions. We're going to get an IR spectrum for this compound, and what we do is pass a beam of IR radiation through the sample molecules. Now, this IR beam covers a wide range of IR frequencies, from low to high values, and all frequencies in between. Now, in this particular example, all of the vibrations in our molecule meet the criterion of changing polarity during a vibration cycle. For each vibration, there's going to be a frequency matching photon in that IR beam. When that photon impinges on the specific vibrating bond or set of bonds, the photon will be absorbed. And this photon absorption is detected, and this event is recorded. Specifically, what happens is every time there is an absorption of an IR photon of a given frequency, a peak is drawn, and that frequency value is recorded. The peak that appears will have a certain size. It's displayed as peak intensity, and a certain degree of broadness. Peaks vary for IR peaks, they vary in their degree of broadness sometimes. Now, when I indicated that the frequency in an IR spectrum, frequency for each peak appearing in the spectrum, is indicated, the frequency unit that is used is not the typical frequency unit that we normally use for frequency. Frequency is normally in hertz, which means cycles per second. But in IR spectroscopy, instead of using cycles per second, that is hertz, we use a quantity that's directly proportional to frequency, and it's called wave numbers. Specifically, it is the reciprocal of a centimeter, centimeters to the -1. Soon we'll show you that this wave number unit is indeed proportional to frequency in hertz. But this is the typical unit that's used in IR spectra. We use the quantity wave numbers, not the quantity hertz. Let's examine now the actual IR spectrum of our compound, the cyclohexane with an external double bond. You can see that there are, well, 1, 2, 3, 4 peaks. I beg your pardon, there are 5 peaks. And under each of these peaks is a basic structural unit. That basic structural unit that's indicated there causes that peak to appear. So if we look at the spectrum from left to right, the first peak we see appears to be about 3,050 units. That's caused by an alkenyl CH stretching motion. This alkenyl CH stretching vibration is absorbing a photon at that frequency, creating that narrow, sharp, small peak at 3,050. The next peak we come to, moving from left to right, is a larger peak. It's actually a couple of peaks. But both those peaks, and they appear about 2950 units, 2950 wave numbers, is caused by the CH stretching vibration of an alkyl CH. All the methylene groups, the CH2 groups in the cyclohexane ring, it's the stretching of the CH bonds that's creating those peaks at about 2950 or so. Moving further to the right, the next peak we come to, the functional group creating it is indicated. It's a CC double bond in the molecule. The CC double bond stretching vibration, absorbing its corresponding photon, creates that peak. It's about 1640 units, it looks like. Then as we move further to the right, the next peak we come to, this is no longer a stretching motion, it's a bending motion. It's the HCH structural unit undergoing a scissor open, scissor closes bending motion. The HCH bending vibration that's creating that narrow peak at about 1450, it looks like. Moving further to the right, next peak we come to looks about around 900. It's actually 2 peaks, a bigger and a smaller one. With respect to the bigger one, that's also created by the bending vibration, namely the HCH of the double bond unit. So it's the alkenyl HCH bending motion that is absorbing a photon, creating that peak at about 900 or so wave numbers.